Hello everyone, Dr. Chem here, and welcome. Let's just jump right into this explainer. Now, we're not talking about the standard TLC your car needs, oil changes and tire rotations. We are diving into the incredibly brilliant, high-tech world of thin-layer chromatography. Picture a cinematic, glowing laboratory. You've got molecular structures floating in three-dimensional space, and colorful, separated compounds glowing under stunning ultraviolet light. That is exactly the world we're stepping into today. We're going to explore how this unbelievably powerful analytical technique separates, identifies, and even purifies the complex chemical mixtures that make up our food, our medicines, and our entire environment. Here is our quick roadmap for today. We'll hit 1. The magic of TLC. 2. Normal versus reverse phase. 3. Two-dimensional TLC. 4. Preparative TLC. 5. High-performance TLC. And finally, 6. Real-world applications. Section 1. The magic of TLC, a molecular separation journey. Okay, let's ground this in physical laboratory reality. The entire process of pulling apart something complex, like an herbal extract, breaks down into 5 really clear steps. First up, sample preparation, which usually just means grinding up your material. Second is application, where you precisely spot a tiny drop of that sample onto your plate. Third, you drop that plate into a solvent chamber and let the mobile phase do its thing. Fourth is detection, often under a glowing UV light or maybe using a chemical spray. And fifth, the actual identification, where we compare those cool separated spots against known chemical standards. It's an elegant, remarkably effective workflow. But how does it actually work? Well, it all comes down to chemical affinity. Think of it as a choice for the molecules. Do they want to stick or do they want to surf? The stationary phase is your solid layer, usually something like silica gel coated on a glass plate. The mobile phase is your liquid solvent, and it gets pulled up that plate purely by capillary action. If a molecule in your sample really loves that stationary silica phase, it's going to drag its feet and move slowly. But if it prefers the liquid mobile phase, it's going to surf that wave right to the top. This difference in speed is exactly how our mixture pulls apart into isolated spots. Section 2, normal versus reverse phase, flipping the chemical polarities. So, in standard normal phase TLC, we use polar raw silica gel and a nonpolar solvent. This means highly polar compounds stick hard to the silica and barely move. But what if the compounds you're trying to analyze just don't play nice with that setup? Enter reverse phase TLC. Here, we completely flip the script. We chemically modify that silica by adding long nonpolar carbon chains like C18, and then we use a highly polar solvent like water or methanol. Suddenly, your nonpolar compounds are the ones sticking to the plate. It's literally like reversing the rules of chemical gravity to solve a totally different kind of puzzle. And no matter which phase we use, we measure our success with something called the retention factor, or RF value. The math is simple. It's just the distance your compound traveled divided by the total distance the solvent traveled. If your spot never leaves the starting line, its RF is 0. If it surfs all the way to the absolute top, it's a 1. But we actually don't want either of those extremes. By carefully tweaking our solvents, we're aiming for this glowing sweet spot right here, an RF value between 0.15 and 0.85. That guarantees our compounds are clearly separated and super easy to analyze. Section 3. Two-dimensional TLC, expanding the analytical grid. Now, imagine you've run your sample, but it's just a mess. You've got spots completely overlapping because the molecules are just too chemically similar. This is where two-dimensional TLC saves the day. First, you run the plate just like normal. Then, and here's the genius part, you take it out, let it dry, rotate the entire plate exactly 90 degrees, and run it again in a completely different solvent system. You're hitting those molecules with 2 totally different separation mechanisms, say polarity first, then hydrophobicity. The result is a highly resolved, 2-dimensional coordinate grid that scatters your complex mixture beautifully across the entire plate. Section 4. Preparative TLC, scaling up for purification. Up to this point, we've only been talking about looking at tiny amounts of molecules. But what if you actually want to keep them? What if you need to isolate a pure compound for a totally different experiment? That's what preparative TLC is for. We use much thicker plates loaded with a heavy layer of silica, which lets us process way more material, sometimes over 100 milligrams at once. Instead of spotting a tiny dot, you paint your sample on as a thick line. It separates into these chunky, distinct horizontal bands. Then you literally grab a scraping tool, carve that purified band right off the glass, wash away the silica in a vial, and boom, you've got a highly purified chemical extract ready to go. Section 5. High Performance TLC. the digitized future of chromatography. All right, let's fast forward to the absolute cutting edge. High-performance TLC, or HPTLC, is a massive hardware upgrade. While standard classical plates use silica particles that are about 10 to 12 microns across, HPTLC uses these perfectly optimized microscopic 5 to 6 micron spheres. Because the packing is so incredibly dense and uniform, your molecular bands don't diffuse or blur nearly as much. You get blazing fast results, often in just 3 to 20 minutes, and a sensitivity that's literally 5 to 10 times higher than classical TLC. Check out these luminous, incredibly compact zones under the UV light. Because the spots on an HPTLC plate are so incredibly tight, it opens the door to computerized densitometric scanning. Basically, we aren't just eyeballing the plate anymore to see if a spot is there. A computer actually scans the exact fluorescence of these bands and generates a hyper-precise digital fingerprint. It tells you not just what is in your mixture, but exactly how much of it is there. It turns a manual chemistry trick into an automated, quantitative powerhouse. Section 6. Real-world applications. Why thin-layer chromatography matters. So why should we care? Well, because this technique is essentially a silent guardian for modern consumer safety. Pharmaceutical labs use it constantly to assay drug purity and track chemical syntheses. Forensic scientists rely on it to break down the exact dye compositions of microscopic fibers found at crime scenes. Environmental labs use the extreme sensitivity of HPTLC to hunt for trace pesticides in our drinking water. And it's absolutely crucial for authenticating complex herbal supplements, ensuring that the label on the bottle matches the actual chemistry inside. As we wrap up this explainer, I want to leave you with this thought. We've gone from basic paper chromatography to digitized microscopic silica arrays that map out the exact molecular building blocks of our world in mere minutes. As these plates get even more advanced, and as the automation gets even smarter, what invisible chemical secrets are we going to unlock next? Thank you so much for joining me on this journey through the glowing, dynamic world of TLC. Stay curious.